All right, all right, all right. Let's get started. Hello, everyone. How are you? Hope you are all well, all safe. And you guys are probably very bored. Like a whole week of math. Like, how did you guys even survive? You're so strong. I don't know. Anyway, it's good to be back. Let us share the screen here. So before we actually, yeah, Ash is like joining two classes. Okay. The homework kept you busy? Okay, that's good. Hopefully you got through it though and you understood everything. So before we begin, some more people are trickling in here. Before we begin, I guess some announcements to make just to keep everyone up to speed. I've been getting questions about exams and so on and so forth. Officially, no decision has been made. So what I've decided to do, and I announced this to my other classes, I've just started to move ahead with my own plans. So tomorrow I'll be going through some workshops and demos and all that sort of things to kind of get the platforms that I want to use for exams up and running. I will give you guys more information on that by Monday of next week. So by Monday, I'll definitely have a way of actually administering the exam. I'll tell you how it's going to look, how it's going to be, how it's going to feel, and I will give you a mock exam to practice with. And then the exam will be like a week after that, right? So you should expect exam 1 to be, say, the 27th. Well, if you're in the Tuesday class, so for you guys, like the 28th. Or we could even just push it to the end of that week. So, I mean, either way, it's not gonna, like I wouldn't grade them until the weekend anyway. So maybe I'll say for my GH section, the exam will be on the 29th, and for the RS2 section, which is this section, the exam will be on the 30th. So maybe I'll just say that. Yes, either way, it's the last week of April. Okay. And I'm guessing I will actually set that in stone. So make a note.
Professor?
Yes.
So how the exam will be?
Yeah, so it will be through online. You're going to basically write stuff. So I'm going to figure out how you guys would actually get to do it. But it's going to be like a fully long form exam, and you guys are going to be doing it, and you'd have a certain time to submit it. And I want to figure out the logistics tomorrow when I look at the demo.
Is there like something like we have to work on the paper and then take a picture and then submit it, or?
Yeah, it'll be something like that.
Okay.
Yeah. So I'll give you all that information next week once I fully know all the details, but I'm going to move forward. In terms of the final, for sure, I can't make any decisions on that because you guys are doing a departmental final. So in that regard, I'm definitely going to have to do with you guys whatever they're doing. But in the meantime, just to get our in-class exams out the way, I'm just going to move ahead with what I wanted to do. Yeah, so that is the first thing. Second thing, the recording for the last couple lectures that I did for this class, they kind of got messed up. So what I did was I took those down and I uploaded the recordings from my other section to the lecture series for this class. There's a little bit of overlap, but it ultimately will cover everything that I covered with you guys as well. So just so you might see some videos in the lecture series for this section that says it's for the GH section. That is actually on purpose because the video recordings just got messed up for you guys somehow. There was a lot of freezing going on, and I was talking about one example when the screen was on another example. Like my equipment technology just wasn't cooperating with me that day.
Are you curving the exam?
No, Not particularly. I don't particularly curve exams. So in general, I do not administer any kind of broad brush curve, like, oh, just bump everyone up a certain percentage. I really grade based on the individual. So I will be looking at your improvement over time and that sort of thing. And so that's kind of how that would go. But I wouldn't worry about curving exams or anything at this point. If you guys prepare well enough and you go through the review that I'm going to post, the exam should be very similar. And I don't intend on making it any harder than I would have made it for an in-person exam. So it's going to be the same length that I would have written it, same level of difficulty. If anything, it might even be a little bit easier just because there's going to be a lag that ensues just because of technology. So I'll probably even make it a little bit easier, actually. But yeah.
So is the exam gonna be during the class time, or you gonna give us a week or something?
Oh, it'll be during the class time. Yeah, that is my envision. So it'll be during class time.
And how long is the exam?
It'll be about an hour and a half.
Hour and a half.
But yeah, as far as specifics like that will go, I will fill you guys all in by Monday, Tuesday next week. Because I really want to know how the technology side is actually going to work. I know what platform I want to use, but I don't know the intricacies of it. So I already registered for some demos today and tomorrow. So I'll have all the specifics and I'll let you guys know by early next week, the latest. And then the following week, at the end of that week, is going to be the exam. So you'll know everything you need to know by then. And the second exam will be pretty much the last day of class. So that's going to be May 15, 16, somewhere around there. And then the final is going to be after that. Yeah. So
Professor,
that's, yes.
I have a question. I had done all the homework, practice problems in the book, etc. Plus the mock exam that you're going to give. Can you give us some extra problems? Because I don't know what else to do to be prepared for the exam, I mean.
Well, if you have the textbook, which I assume everyone has,
Yes.
I would actually practice, especially if you feel like you feel shaky on a certain topic or something like that, I would practice more problems from the textbook itself, because I'm going to be looking at the textbook for the level of difficulty that I would assign to you. So if you look at the syllabus, there will be suggested problems, and what you can do is you can go into the textbook, and you might notice in a certain section, for example, let's say a suggested problem was problem 15, but all problems between problem 10 and problem 25 were of the same form, but they're only suggested problem 15, and maybe your homework only had problem 15. What I would do is practice from the rest of the problems in that group. And you can practice with odd and even problems as well. So the textbook would be the first line of defense in terms of just straight up practicing problems. I would start there. And if you finish all the problems in the textbook, that's another story. I guess if you're one of the people who finished all the problems in the textbook, then we can talk about something else. But that's probably what I would do. Just go to the textbook, and if you only did a few problems from each section, just do the entire section, do all the problems from the section. That will actually give you a pretty good preparation, because the level of difficulty I'm going to test you at will be at the textbook or slightly lower.
Okay, sounds great.
So yeah, as far as really preparing for the exam will go, well, my mock exam will help you with that. You'll know the structure of the exam, how long it's going to take, what kind of questions I'm going to ask. So I'm going to give you a mock exam, and I am going to make a very similar exam, which I'm pretty much like going to swap out the problems. So if there's a problem that asks you, oh, show that these series converge, I'm going to ask you a question in the actual exam, show that these series converge, but that particular series will be different. So you'll know about the structure, definitely.
What are the topics?
So exam 1 will cover everything up to the end of series.
Okay, meaning chapter 8 and 10.
Yes, right up to 10.10, I want to say. So I actually have a physical textbook here. So yeah, well, we did a couple things in chapter 7, but yeah, chapter 8 and pretty much all of 10. Yeah. So those 2 chapters. So all your integration and everything I taught you with series, including Taylor series and their convergence. And then the second exam would cover everything, parametric equations, polar coordinates, and all the stuff that we're going to start today, which we're in for a treat today. As you can see here, we're going to talk about the 3D. We're going to start doing math in 3D here. So that'll all be exam 2. So exam 1, everything up to series.
Professor,
So,
I have a question.
Yes.
Homework for chapter 12.1 is due on Saturday. Can you extend that until Monday?
Oh, homework for 12.1? Sure,
Yes.
I'll extend that. I'll probably actually extend it until like the end of next week or something like that. Extend homework for chapter 12. Okay, yeah, so I will do that. So we're going to start chapter 12 today. So of course you wouldn't be able to do that in a couple of days, or at least I wouldn't want you to do that. Yeah, was there anything else I wanted to announce? I think that was it. So exam 1 for you guys is going to be around the 30th. So it's Thursday, 2 weeks from now. I will give you very specific information regarding that exam Monday or Tuesday of the following week. So by the 20th or the 21st, whichever time I see you first, you'll have very specific information about the exam, which you will be given a week later.
Did you decide how many questions you're gonna put on the exam?
No, I don't know, but 5 or 6. It'll be around the 5 to 8 range, something like that. But yeah, so you'll know specifics about the exam by early next week. So you're going to see the mock exam. You'll know how long it is. The recordings for some recordings for the GH section were added to this lecture series because the video got messed up. But everything should be up to speed now. And yeah, so I think we can start. Yeah, and I see a comment here, someone asking about group studying, like a Zoom study group. I know you guys can set that up yourselves if you'd like. But yeah, let's actually move on. So we have an interesting topic today. And for this part of the class, when we're actually going to be doing the math, what I would say is I'm going to turn off my video because you don't really need to see me anyway, because sometimes I realize that there is like conflict when it's trying to stream the video and me writing on the tablet. So you're not going to see me, but don't be afraid. I am here. Okay. And there we go. And I assume everyone can see the OneNote document. Okay. All right. So we are going to do something which is interesting. Now, this is where calculus really starts getting interesting as far as I felt. Let's see here. I see people trying to set up a group study. Maybe save that until the end and try to set up the groups at the end. Okay, no problem, no problem. It's good that you're actually even looking into this, but let's everyone focus in right now on the actual topic. And if you guys want to set up study groups, you can do it towards the end. Okay, so we are going to start chapter 12. It's titled the three-dimensional coordinate systems, which is a misnomer because we only actually talk about one coordinate system in this section, the rectangular coordinate system, just so that we know about some phrases that I would use here. We're going to talk about three-dimensional space, which I might refer to as 3D space or 3 space or R3. These are all referring to the same thing. In general, n-dimensional space is sometimes called n space. And whenever we're using the coordinate system that I'm going to be talking about right now, which is the rectangular coordinate system, people normally refer to it as the Euclidean n space, named after the mathematician Euclid. So talk about 3D or 2D, we're normally talking about the Euclidean space, the kind of space that we've been used to, that we've been working with in terms of the rectangular coordinate system, okay? So just to remind you of the 2D system, we looked at this last week as well. How do you locate a point in the rectangular coordinate system? So in 2D means, there are two axes, there are two variables. One is normally thought of as a dependent and an independent variable. These were X and Y. 2D means there are two variables. And if we had to locate a point, say the point 1, 2, what we did was we found 1 on the X, we found 2 on the Y, and this went across and that went up, and this is the location of 1, 2. How we're going to look at 3 space is going to be very similar. The difference is we are going to throw in a third variable. So in 3D, we have 3 variables, and instead of rectangles, as you would see here, we actually form boxes, which is just a higher dimensional rectangle. So 3 space, how we will illustrate it on paper, that's what I first want to talk about, and we will sketch it like so. There will be a vertical axis, and then 2 going off to the side like here. This is where we'll put the x-axis, this is where we'll put the y-axis, this is where we'll put the z-axis. So when you're looking at 2D space, x and y, what you can normally do is imagine that here's your eye view. We were normally looking down at this space. In 2D, we have a bird's eye view where the z-axis was normally pointing out of the page straight up into your forehead. So here's the x, this is the positive x, and of course the negative x will go back here. So these are where you have the negative x's. Over here going back, you would have the negative y's, and you can actually move down. So this is how we position the different variables together. And just so that you know, whenever a problem in an exam or something would talk about positional things, so they will say, oh, it's to the right of this or to the left of that, it is always assumed that you have the variables arranged in this particular fashion, right? So it's not the only way to actually sketch this. I know of other ways to sketch things like this where I see people sometimes do the x and y's they normally do, and then they think of the z as coming out here, but we are not going to do that. We are always thinking of the positions as demonstrated here, okay? Can you have 4D graphs? No, we cannot draw those. There are different ways to visualize 4D, but no, not as a picture. The best we can do is do 3D. And in fact, even in 3D, sometimes drawing it on a 2D paper, it's going to be hard to visualize sometimes, but once we go 4 dimensions or higher, we really think of our spaces as something as R3. In the sense that we don't think of it as some visual way. We think of it as just a list of coordinates and functions. And we really use the math to be our guide because we will no longer be able to visualize things in the traditional sense. Okay, but that being said, and I have some things to help you learn to visualize 3D here. But that being said, how we would actually locate points, right? Yeah, you tried to ascend to the next dimension. Yeah, but even in physics, well, in applied math and in pure math, yeah, if you go much farther in math, eventually you will be working in 4 dimensions and higher. If you're a math person, you'd be working in infinite dimensions at times, but at that point, you definitely can't sketch anything. What we can do sometimes in higher dimensions is sketch things that are, to compare it to what we would recognize is like a shadow. You know how you can be a 3-dimensional object and you cast a 2-dimensional shadow on the ground? There are times when you can think of a 4-dimensional object as casting a shadow, which is 3 dimensions in our universe. And we can really draw a picture of a shadow of something in the 4th dimension. But drawing something directly in the 4th dimension, nah, our brains cannot go that far. And we definitely can't represent it on a 2-dimensional piece of paper. Okay, how would we locate things in 3D? Actually, very similar to how we do it in 3D, in 2D, actually. We use the rectangular coordinate system. So for example, if I wanted to locate the point 1, 2, 3, the first coordinate is the x coordinate, the second coordinate is the y coordinate, and the third coordinate is the z coordinate, right? And I mentioned this in the text all over the place, but just so you know. So basically you would do as normal, find 1 on the x-axis, find 2 on the y-axis. And so there's a line emanating from the x that is parallel to the y-axis. There is a line emanating from the y that is parallel to the x-axis, and they will meet at a point in the xy plane. Then what you would do is you'd find the point 3 on the z-axis, and this pretty much rises vertically up until it is in line with that point 3. So this is the point 1, 2, 3. And you can imagine that there is a rectangle here. So there's like really a box here where this is going to be the corner of your box. That was actually not drawn very well. And so here we go. And so the box is really has its corner on the Z, and that's the box here. This line here I was drawing was running along the diagonal of the top of the box, right? So you have this box. Yes, you have to make the sound effects when sketching these things. It really helps. So yeah, it's a rectangular coordinate system, but a higher dimensional rectangle. It is actually a box, and that's how we can locate points in 3 dimensions. Now let's start to talk about some of the vocabulary that we will use when talking about 3-dimensional space. And to get you kind of get your bearings straight, I will use a room to illustrate how this is going to actually look. So your x-axis runs here, your y-axis runs there, your z-axis goes straight up. So if you were a little man in a room, so you can stand a room and you can face a corner. So this is you, right? And let's say you are looking directly at the corner of the room, face the corner, right? So you are in a room, you are facing the corner, right? So you're standing in the room, you're looking at the corner, okay? If this is the corner on the floor. You can imagine that the x-axis is running along the floor, along the left wall. The y-axis is running along the floor, along the right wall. And the z-axis is going straight up to the roof in the corner. And so here you see that this wall is bounded by the x and the z-axis. This wall is bounded by the y and the z-axis. And the floor that you're standing on is bounded by the x and the y-axis. We therefore call these guys the xz plane, the yz plane, and the xy plane. So up until now, you've been doing your math in the xy plane. That was our universe. Right now, we've added an axis to our universe. So our universe has expanded from 2 dimensions to 3 dimensions, but this is the situation. Now, if you are in a room and if you are the guy standing in the room, what you are standing in is called the first octant, okay? You will notice that if we just imagine these planes going on forever, extending on forever, you would actually split space into 8 compartments. there's the room that you're standing in, there's the room behind the right wall. This is the second octant. There's the room that's beside that room, behind that wall over here. That is the third octant. There's the room behind the left wall. That is the fourth octant. And then if you imagine that this is sort of a two-story building, there's a room below you in the floor below you. That is the fifth octant. The room beside that is the sixth. The room over here would be the seventh. And the room underneath this room would be the eighth, right? So this kind of is a nicer visualization there. So you are the little man standing in this room. You are on the second floor, right? A lot of our math is going to be done on the second floor of this room, right? So that's where you're standing in the room looking at the corner. There's a room over here, there's a room over there, there's a room over there, there's a room below that, there's a room below here, there's a room below there, there's a room below there. In the room that you are standing in, you are on the second floor at the top. That is called the first octant, labeled number 1 here, all right? So octant for octave, right, the 8. And so there are 8 compartments. So it's not like quadrants that you had in 2 dimensions. So the plus and the minus sign represents the signs of the x and y and z coordinates. So the first octant is the space in which your x, y, and z coordinates are all going to be positive real numbers. If you move over to this room, notice that you're in the situation where the x-axis is negative, but your z-axis and your y-axis are positive. So your x will be a negative number over here, a positive, and your y and z will be positive numbers. Over here, your x is a negative number, your y is a negative number, your z is a positive number, and so on. So the signs here refer to the signs of the actual coordinates, the numbers that they can take on. Okay, so the first octant is the most important one for you to know. I've never really seen a problem where in a calculus 2 or 3 course where they ask you to do something in the 5th octant. Oh, imagine that this object is in the 5th octant. It doesn't really happen. If an octant is mentioned, the first octant is going to be the one that's mentioned by name. So that's the one you should be most familiar with. So just the room that you're standing in, that's how you want to visualize this. Okay. So yeah. So now we're thinking of 3D space as this 2-story building where we are on the second floor. And our universe was just this little, I don't know what color that is, a weird green. This was our universe before, but now we've added more dimensions. So that's what things will actually look like. And the points here, so here we use 3 coordinates. So these are still called coordinates. And the first one is the x coordinate, the second one is the y coordinate, the third one is the z coordinate, respectively. So yeah, that's just being able to visualize. And again, just as always, I will be posting a PDF version of these notes. So you don't have to worry about copying this down right away in real time. But ultimately, I do want you to take your own notes. Okay, so moving down. So now you know about points in that thing. Let's start to actually visualize some objects in 3-dimensional space, just getting us used to how things would look. Now, if you were in 2D and you saw something like, if you were in 2D and you saw something like x equals 1, and you wanted to draw a graph of that, of course, you'd have the x here, the y here, and it'll just go through 1, and it'll be a line. It's actually just a line. So this is a line in 2D, a vertical line more specifically. However, in 3 dimensions, if I were to ask you what is x equals 1, or y equals a number, or z equals a number, anything of the form x equals k, y equals k, z equals k, what would that actually be in 3 dimensions? So I want to actually draw some examples of that here. Let's have a little bit more space here. Okay, so okay, so let's actually get our sketch on, learn to visualize some things. Okay, so 3 space, we will always represent it like this. Oh, that was bad. Right? So x equals 1. How you'd represent this is first you find where x equals 1. So that's where x equals 1. Now, of course, in 2D, it's just everything running along this line, right? But you'll notice here, if I move directly vertically above that point, the coordinate of that point would also have x equals 1. And if I move directly below that point, that coordinate will also be have x coordinate 1. The y coordinate would actually can be potentially different. And even if I move along to the left or the right here, everywhere along this line will have coordinates x equals 1. Everywhere above that will have coordinate x equals 1. Everywhere directly below that will have x equals 1. So you actually have a different object here, and it is called it's called a plane. So you will have like a flat sheet that extends forever in all directions, and that is our x equals 1, right? So there's just like this flat two-dimensional thing that extends along x equals 1. It's completely vertical and just slicing through x equals 1. So you obtain a plane here. Let's kind of move this out of the way. Can I move this picture? No. I don't know. Maybe move this whole thing down. This, well, I just want to get a better view here so you can actually see the equation that I was sketching. Okay, there we go. Okay, so that would be x equals 1. No, this is 1 point. The point 1, 0, 0 is just a single point in x equals 1. So the point 1, 0, 0 is literally this dot right here. But there are other points in here. So I can have, for example, 1, 2, 0. Right? I could have over here, this would be something like 1, 0, 3. Right? So this plane is a sheet that involves all possible coordinates where the x component is 1. The x coordinate is 1. Okay? Right. So moving on, x is negative. It extends, it goes on forever. So this actually extends in all directions. This keeps going up. This keeps going forward. This keeps going back. It extends forever. Yeah.
I mean, like, what if the x is equal to -1? Is it go to the other side?
X equals -1 is not on this plane. That's over here.
Oh, okay.
Yeah, x equals -1 would be, if you continue going along the x-axis, there's a point over here that's -1. It's not going to be on your plane, right? So because your x is always going to be 1, it's always going to be a constant. Similarly, I can talk about y equals -2, and I can draw this guy here. This is x, y, z. So of course the axis, this continues the -y, that will continue the -x, that will continue the -z's, and y equals -2 is going to be a point over here. So I'm going to pick the point -2. Y equals -2. Remember, it's going to be like a horizontal line if we were looking at the bird's eye view, and there's just a sheet that actually is parallel to that. Right? So that is behind your first octant. It covers, it slices through the third and the fourth octant, and of course the 5, 6, 7th and the 8th octant. But it's just a sheet extended forever in all directions. It keeps going, but it's like vertically upright. And I can talk about this other one here, this Z equals 3. Maybe I'll give this a little more space. And Z equals 3. So, so you'll draw your axes the same way. Boom, boom, boom. Find where Z equals 3. And then there's just a flat sheet hovering in space. It is parallel to the XY plane. And that is, I don't know, Z equals 3. Okay. So these guys are all planes. If you have your X and your Y or your Z equal to a constant, these guys are just flat sheets that are perfectly flat. You will learn about a notion like slope in higher dimensions, but they will always kind of have the same slope as would be predicted by something called normal vectors, but that's for another time. But that's what that would look like. Moving down, what do you guys think this would look like? Y equals X. Y equals X is a cube. Some interesting responses here. In 2D, what does Y equals X look like? Start there, Y equals X in 2D. It's just a line. Right, you don't think of it as two lines being intersected. It's just one line, right? Just going through the origin at a 45-degree angle, right? So that's the line Y equals X, right? You have the same idea, except now you can imagine that there's a Z-axis being pointing out the page, but this line is just rising up. So it's again going to be a sheet. So in 3D, which is how we're going to be visualizing it. It's something that's coming through here slanted, but again, it's just a sheet that's being slanted. But the line, it contains the line Y equals X. So this is the line Y equals X in 2D. So that's that guy here, right? But it's vertically upright, and it's just a sheet slicing through that. So it's not a horizontal sheet, it's actually vertical in relation to how we draw the axes here. What about x squared plus y squared equals 1? What's that? What would that be? X squared plus y squared equals 1. Any guesses? A sphere? How would you get a sphere from that? So of course in 2D, we know that that's a circle. In fact, that's a circle of radius 1. Right, so Ash is kind of getting it here. The line turns into a plane. It's not completely how you want to think about it, but yeah, I think intuitively I know what you're trying to say. So if you are here, I still have a red. So we know in 2D, this guy is just a circle. Let's make it a red circle of radius 1, right? Now, that circle, if I were to draw it in 3D, he's just going to be this guy that's on the floor, right? So there's going to be like a circle of radius 1 on the floor. But notice that that is when your z is 0, because the xy plane is when z equals 0. I don't recall mentioning that before, but equations for the xy plane would be z equals 0, for the yz plane would be x equals 0, for the xz plane would be y equals 0. I mentioned that in the notes. But what you will notice now is all points directly above that would also obey the equations with x's, because here z isn't mentioned. So this must work for all z. Okay, and that is actually an important part. And I'm going to tell you how we kind of deal with that in a bit. So basically the idea is, sure, when z is 0, we should see a circle if we're looking down at a bird's eye view, but we should also see a circle if we're looking at z equals 1 with a bird's eye view. We should also see a circle if we're looking at z equals 2 with a bird's eye view. And z equals -1 with a bird's eye view, and so on. And what you get is you have all these circles that are lying right on top of each other. And you get, yes, a cylinder. And it's, of course, it's actually completely hollow here. But you just have a cylinder. If you were to take any cross section, any slice through this thing that is parallel to the xy plane, you would actually see a circle of radius 1 with center of the origin. If you were to look down, right, so if we look down, looking down with a bird's eye view, we're going to see this guy. Okay, but now it extends, it runs along the z-axis. A guy like this, yes, a technical term for it is a cylinder. So you won't actually get a sphere, but we are going to talk about spheres, but hopefully you'll be able to visualize that somewhat. Now, we are going to talk about spheres, as you can see right here, but before we talk about spheres, we need to have a notion of distance. And it turns out that our notion of distance is pretty much the same as it's always been. In our rectangular coordinate system, if you have, so remember that we derived the distance formula back in 2D in using Pythagoras' theorem, right? So the truth is, if you have 2 points here and you want to find the distance between those 2 points, call that D, what you can do is you can create this plane triangle hovering in space that slices through these 2 points. And Pythagoras' theorem can tell you that, oh, the difference in the x's and the y's and the z's squared and square rooted, but well, that's how we kind of use it here. So remember in 2D, just to kind of explain, if you wanted to measure the distance between 2 points, right, this was D. What we did was we created a right triangle. The length here would be, say, x2 minus x1 is the difference in the x values. The length here would be y2 minus y1, the difference in the y values. And then Pythagoras' theorem tells us that if I take the x2 minus x1 squared plus the y2 minus y1 squared, we actually get the distance squared. And so by taking the square root, we got a distance formula that looked like the square root of x2 minus x1 squared plus y2 minus y1 squared. Once we add another axis, the z just actually comes into play just as it normally would, because that Pythagoras argument, if we project it right down into the xy plane, we would use the Pythagoras argument here, but then projecting it up now into the z plane, we get another right triangle where we can use the Pythagoras argument. And so you actually get a formula that looks very similar to what we would have in 2D. Just add another variable. When we do something like this, we can say something generalizes naturally. So if there's a formula that we have in one context where to make it more robust for a new context, you kind of just add something very symmetrical to the formula. We say it generalizes naturally. So the formula for distance generalizes very naturally in 3 dimensions. And we just basically have a different distance formula where we just add in the z component, the distance of the z. And this actually works in 4 dimensions and higher. Now we won't be able to visualize it necessarily, but we could add in the difference of variables in the other section as well. That being said, a sphere, you can think about it as the set of all points that are equidistant from one point. So I can pick a point, call it HKL. I want to find all possible points that are at a distance R from this and from looking in all directions. So basically, by distance formula, you want all x, y, z that are r units away from HKL. This means your r is going to be the square root of the difference of these guys, x minus h squared plus y minus k squared plus z minus L squared, and then squaring both sides, you end up with this formula here. So this is the formula for a sphere. So what does a sphere look like? It looks like this. You have to have 3 all variables accounted for. And that also generalizes to higher dimensions. So if we had another coordinate, call it the w coordinate, then there would also be a w minus something all squared equals r squared. And that is how we think of a sphere, just by applying the distance formula. Let's do an example. Show that this guy is the equation of a sphere. What is its center and radius? So basically, to show that something is the equation of a sphere, what you want to do is show that you can write the equation in this form. Once you identify the h, the k, and the l, and the r, you can talk about its center and radius. And how do you guys think we would go about showing that this can be written in that form? Move the terms to one side. So we have x squared plus y squared plus z squared minus 4x plus 2y equals 0. And then what? Complete the square. right? Complete the square. That thing that you learned in algebra class that you literally use forever, right? So it's one of those things that keep coming up. So you need to know how to complete the square. What you would do is you would group the x's, you would group the y's, you'd group the z's. Take half the coefficient of x and square it. So that's -2 squared. You're going to add that. Take half the coefficient of the y term and square it. You add that. Half the coefficient of z and square it, you get 0. It's not going to make a difference. But you have to add it to both sides because it is an equation. Now, this guy here becomes a complete square. It's going to be x plus the guy inside here, -2, all squared. Y plus the guy inside here. And this technically I can think of it as z minus 0 squared to be a little bit suggestive. On this side over here, I have 5. So that has the form of a sphere. What is the center and radius? Right, 2 minus 1, 0. Radius is the square root of 5. Okay, because this I can think of as the square root of 5 squared. And so it's r squared on this side. Yeah, so that's okay. So of course, one thing that is going to be important is given a bunch of, given an equation with all these variables, how do you know what object you're looking at? Are you looking at a plane? Are you looking at a cylinder? Are you looking at a sphere? These are things you're going to need to know, and you're going to need to have positional awareness of them. So completing the square and all your algebra tricks from before are still very, very useful here. Moving down, let's talk about regions in 3 space. Okay. So what would the region, and this is in R2, so this is in 2 dimensions here. What do you think the region y is less than or equal to x looks like? So we are in R2 here. How do you sketch a visual representation of that inequality? And it's called a region because it doesn't have like just one thing that satisfies it. There's like a whole shade below y equals x, right? So you imagine that this inequality is an equal sign. You would sketch what it would look like. So this is y equals x. And the region represented here is all points where the y value is less than or equal to the x value. So this is everyone down here. Right? That's that guy. Now this was mentioned in the other class, so I'll just mention it for you guys as well. How would you represent y is strictly less than x? Right, dashed line. Right, so to show that the line itself is not included, you can just use dashes. And you'll still shade it, of course. Okay, so, all right, so you guys know the concept of doing this in 2 dimensions. Let's try some 3-dimensional stuff. What does this look like? So this says First Octant. Ideas. What are we looking at here? 1/8 of a sphere. Okay, so normally x squared plus y squared plus z squared equals 1 is a sphere. When we say x squared plus y squared plus z squared less than or equal to 1 means we want all things that are a distance of 1 or less from the center of the sphere, which means I fill in all the inside of the sphere. However, since we're restricted into the first octant, this is 1/8 of space, of three-dimensional space. We only really get 1/8 of a sphere. Now, how would you visually represent this? Now, here's an important thing. In general, when you start to talk about regions, even if it's talking about a very small part of a region, you would tend to want to sketch the whole region and then kind of piggyback off of that. So me recognizing that this is a sphere, right? X squared plus y squared plus z squared is a sphere. Is a sphere. I don't know. Is that a different color? Right. So what I would do is I would actually draw the whole sphere. That's how I would actually start out. So X, Y, that force of habit. That's the Z. The Y is down here. Now, how do you draw a sphere? Basically, you draw a big circle. So and then pretty much you kind of draw in its equator. So and it's hard to do as well on the tablet, but I tried. I think that's actually pretty good. Now, what you want to do is now you start cutting off the sections of that the object that you want. So I only want the part that lives in the first octant, which means the YZ plane cuts off this part of the sphere. The XZ plane and the YZ plane will cut off this part of the sphere. And the XY plane is going to cut this part of the sphere. So I pretty much have this object here. So this is the object that we have here. So boom. Boom. It's not hollow, it's filled in. How do I know it's not hollow? Because of the less than or equal to. So it's a region, right? So it's just like here, I know I need to shade in because of the inequality sign. If it was just an equal sign, it's just actually the line. If this is equal to 1, I know it's hollow. If it's less than or equal to 1, it's actually filled in. So it's actually the entire object here. So yeah, it's this whole guy. Okay. So that is the object that we're talking about. So it's just basically like a wedge, 1/8 of an orange or something. Yeah. Yeah, the dashes represent that this is a line that is, I'm looking through the object. So this is like to the back. Right, so really what we're seeing is like there's a wedge here. Right. So this over here is your xz plane. Yeah. So dashes just means you're looking through the object. Right. So yeah, that is our sphere. In the part of the sphere in the first octant that's filled in. So yeah, here's another one. And this question was actually a lot easier to ask about this, the object above. But I'll have you guys thinking about it anyway. What about this one? So look at that region. So it's 1 less than or equal to x squared plus y squared plus z squared less than or equal to 4. However, my y coordinates, I only want to consider ones where the y coordinate is negative, and I want to consider where the z coordinate is positive. This is in R3. What you guys should take away from this is that I'm talking about the guy that's in the 3rd and 4th octant. Right? That's what's being described here. And we'll talk later about actually talking about polar coordinates. It's like a bowl. Okay, so what we would do here is realize that this really means that there are 2 things going on, right? So there's one region where it's that. So this reminds us of a sphere. And we also have x squared plus y squared plus z squared less than or equal to 4, another sphere. So there are 2 spheres here. They're both centered at the origin, because we know from those equations. One has radius 1, the other has radius 2. So in the spirit of what I mentioned earlier, when it comes to visualizing this, what you want to do is you definitely want to draw the objects in their entirety first. So the first order of business would be for me to actually draw the axes. And I'm going to draw these spheres. So there's one sphere. We know it's centered at the origin because this is x minus 0 squared plus y minus 0 squared plus z minus 0 squared equals 1 squared. It fits the form where the h, k, l are 0. And this is 1 squared, so that's radius is 1. This 4 is 2 squared, so the radius is 2. So now I have a sphere of radius. I have a sphere of radius 1, right? So I'm going to go down here and I'm going to sketch that. Put him here. So remember how we do that? You just draw like a big circle. Draw in your equator. then you would have, make it a little thicker. So that is my circle of radius, my sphere of radius 1. Then there's another one that's bigger than that. I don't know why I always put the bottom like that. Then there's another sphere of a slightly larger radius. And he will have his own equator. Okay, so I have one sphere inside the other one. Now what do I want? Well, this is the negative x-axis here. This is the negative y-axis going off there. This is the negative z-axis going down there. Now what I want to talk about is all the situation where all the points where the y-coordinate is less than 0. So it's not going to be in the first octant or the second octant or the eighth or the fifth or the sixth. It's going to be everyone behind the x-axis. So it's the guys over here. Furthermore, I want the z to be greater than or equal to 0, which means it's everyone above the xy plane. So this tells me that I want to be behind x-axis. Now, of course, that word behind really just means in relation to how I drew the axes. So it's very important. When I say to the right of or to the left of, I'm assuming that we're drawing the axis in this way. And z greater than 0 means we're going to be above the xy plane. So behind the xz plane is probably a better way to look at this. So now I'm just going to go in and start to, and this will have radius 2. It's radius 1. And now I just go and I fill in the parts of the sphere that I want to actually take. So there is something that's cut off by the xz plane, which is going to be this guy. Boom. And he's going to go down to here. Boom. 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 And this continues to go down here. Boom. So when the xz plane slices through it, that's going to be the cross section. This is going to be the inner part right here. Boom. Okay. And then it's just the outer sphere. So it's like half a bowl. Or some people in the other class are like, it's a quarter of an avocado with the cereal would fall out. Yes. But yeah, that's what this guy looks like. So it's this object right here. Yeah. Well, your drawing I should be aware of what you're sketching. But no, everyone's drawing isn't going to be amazing. That's a given. But you do want, I should be able to understand what you're drawing. But this is a good rule of thumb. Draw the full figures and then slice off what you don't want and leave what you do want. So that would be the object there. And this is a question to think about. So I described this region with inequalities like that. Could you think of other inequalities in applying polar coordinates to actually describe the same region in a different way? That might be something else. Polar coordinates in higher dimensions is called cylindrical coordinates, by the way. And when you get to the next class, you'll see why it's called cylindrical coordinates. Higher dimensions, greater than or greater than 2. Okay, so hopefully that was, everyone kind of see how that worked. But yeah, that's how you would sketch that region. Being able to understand the regions that you are in three-dimensional space is going to be very important, especially for the next class. When it comes to setting up a lot of problems, you'll have to actually know how the region looks even before you start to set up the problem. So now you guys probably think that integration is hard and all that good stuff, but there's going to come a point where you're not even going to be able to start the integration until you actually are able to draw a three-dimensional figure, figure out what part of the figure you want to integrate over, and then do the integration that way. And the integral itself is going to be iterated. Yes, I'm going to post the notes for this, as well as the video. Right, so that's that. I think that was all I wanted to talk about in this section. There we go. Right, so that was the 3D space, how we look at it. We draw it in this way. If you're a person standing in a room looking at the corner, we imagine that you are in the first octant, but there are 8 spaces that this cuts up three-dimensional space into. And whenever we measure things in this rectangular way, we refer to as Euclidean 3 space. A lot of things that we knew as lines or curves before, they're now like planes or cylinders. So this was a circle in 2D. From now on, it's not a circle. This is actually a cylinder. The two-dimensional thing was the shadow. You've only been seeing a shadow of what was real up until now, but it's time to pull the wool from off your eyes. X squared plus y squared equals 1 is a cylinder. It is not a circle. It was circle in a very limited point of view. We are expanding our points of view here. We also want to know how to measure distance. That's going to be important. Talking about spheres as a consequence, that's the equation of a sphere. And this is the higher dimensional circle. And spheres in much higher dimensions actually look pretty much the same. And it's one of those things, going back to a question that was asked earlier, can you visualize things in 4 dimensions? It turns out you can mathematically show that a sphere is the only thing that you can visualize in multiple dimensions, because spheres in Euclidean n space, they always actually look the same. So what does a 4-dimensional sphere look like? Pretty much the same way a 3-dimensional sphere one looks. But that is by far a rare exception. Drawing regions, knowing about how to get solid objects or surfaces in 3 space is going to be a very important thing. You might have to sketch a couple of those for exams later in this class, but this will actually be a very, very important part of the problem solving process in the next class in Calculus 3. A lot of things that we are doing, a lot of the math that we're doing, it will be in relation to objects that we want to look at. So we're not just going to be doing integration out of context. We're going to be doing integration on an object, differentiation on an object, looking at a certain tangent plane in relation to an object, and so on and so forth. So we do need a positional awareness and just being aware of how structures would look in 3 dimensions, which in later sections in this class, I'll talk more about this. But in Calc 3 is where you're really going to need it, and you're going to have to be pretty good at doing this stuff. You don't have to be the best artist in the world, but you need to be able to draw something well enough to know position. Oh, this is to the right of that. This is above that. This is below that. This is like a part of a sphere. This is a part of a cylinder. You need to be able to recognize what you're looking at. So you should be able to go from equations to some sort of visual representation of an object that you want to talk about in 3 dimensions. Super important. And take a sip of my coffee here. And in that regard, the next section becomes very important. We are going to talk about vectors. So vectors, they are indispensable when it comes to describing objects and motion in space. And we're actually going to be talking about vectors from a very basic point of view, but they will be very, very muy importante in the next class to describe curves that you want to talk about, to describe objects that you want to talk about. We will often be using vectors to describe space, to describe motion, to describe all sorts of really neat things. So I want to make sure that you guys have a basic understanding of vectors. I think most students would have seen something of vectors that I will be talking about here. So it's probably going to be a review for a lot of you guys, but I do want to get up to around this example here. There's a few more, but with the last class, I stopped around there. But yeah, vectors, super important. We need to know what they are and how they work and how to do math with them. And we are going to really start to run with this. We're not going to be talking about curls and gradients or divergence in this class, no. But we will be talking about the dot product and the cross product. Curls and divergence and all that good stuff comes in the next class. That's when you're studying vector calculus. Okay, but we do really need to know what a vector is on a basic level. It is a quantity having both magnitude and direction. Geometrically, we represent it with an arrow or a directed line segment. So me drawing something like this, me drawing something like that, that is a vector, a geometric representation of it. Now, we want to name some things here. The tail of the arrow, you can think of as the starting point. This guy, this here is called the initial point of the vector. Where the arrowhead ends up, this is called the final point of the vector. Clearly, you can see the vector is pointing in a certain direction. Now, we'll talk about how to describe what direction it's pointing in later on, but also with this arrow, you'll notice that it has a length. So this is the length or the magnitude, right? So this is an object that I can describe that has length and a magnitude. It also has a direction. It's pointing up and to the right, right? There's an associated direction with our vector. Quantities that don't have direction, they only have magnitudes associated with them. We call them scalars. For us, a scalar is basically just going to be a number, a real number. So a 2 or a 3 or a -7 or pi. These are all scalars. They don't really have a direction to it. Like if I say, oh, 3, you know, like what direction is it moving in? No, it has no direction. However, if I say, oh, there's a vector, there's a direction associated with it automatically. And this is called the final point or the terminal point. This is called the initial point. I said all this in text here, but I just want you to see what these guys are. So this here is the vector. Now we can name vectors, and we can name it either by the points in which they hit, or we might give it another name, usually with a lowercase letter. Now, if we give a vector a name, there are two conventions. One, it's using a bold font. So if I use a bold font, chances are I'm talking about a vector. However, if you're someone writing something down by hand, we usually just put a little arrow over it. Now, if it is the case that, someone got kicked out. Okay, they're back in. If it is the case that I have a vector that starts at a point A and then ends at a point B, so this is the starting point and that's the terminal point, then I might refer to this vector as AB and put an arrow going from the A to B on top of it. I might also just give that a little name. I'm going to call this vector little a. Now, to emphasize that little a is not just some number, I also put an arrow over that, which I often write like that. So it's a very common thing to write vectors in this form. So if A is the initial point, and B is equal to the final point, I can name it like the vector AB, or give it another name. And you indicate that it's a vector by putting an arrow over it. So in other words, A is not the same as A. We'll technically think of this as a scalar. It's just a number, a magnitude, whereas this we know is a vector. And these guys are very different. Okay, now let's talk about equality of vectors and position vectors. Two vectors are considered equal if they have the same magnitude and direction. So yeah, you can name it whatever, like V with a line. Yeah, you can name it whatever. So you could use V with, you mean like V with just a bar? No, we don't use bars. That we tend to think of that as like an absolute value of V, or mean V. So we actually write arrows. So you might write a half an arrow. So instead of writing both arrows, it's acceptable to use a half an arrow, but yeah. So bars usually mean something else. Let's see. Yeah, two vectors are considered equal if they have the same magnitude and direction. So let's say here I'm in my XY plane. I have a vector here that has a length of 1 and moves up, has a length of 1 and it moves up at 45 degrees. And it has length 1. Then any other vector in space, no matter where it's located, if it moves up at an angle of 45 degrees, and has length 1, these guys are considered to be exactly the same vector. We think of these as the same vector. The position, the initial position of the vector is not different, does not matter. So if I call this vector A, then that guy's actually also the vector A. It's not thought of as a different vector. Now, there's one thing that is going to be different here, and that is the idea of a position vector. So all vectors with length 1 moving from bottom left to top right at 45 degrees are considered to be the same vector. So sometimes, though, it's necessary to have a common reference point for vectors, and oftentimes this is going to be the origin. Whenever we emphasize that a vector has initial point the origin, specifically the origin, we call it a position vector. So I could have the vector, so I could be here, and over here, I just have a vector A, and I could have him over here as well. That's the vector A. Once I fix him to the origin, this is the position vector A. Okay, so it's called a position vector, and that's because it's actually coincides with coordinates very well, and I'll mention that in a little bit. But yeah, vectors, they can live anywhere in space, and as long as they have the same magnitude and direction, they're considered the same vector. Sometimes we want to think of vectors in a certain position, namely the initial point, the origin. We call these guys position vectors. Now let's look at mathematical notation. We can write a vector much like we write coordinates. The difference is we use angled brackets for the coordinates. So if we have a position vector whose terminal point is A1, A2, so I could have, so to just visualize this here, this I can think of as the point A1, comma A2, and that's a point. If I have a position vector that starts at the origin and hits that, I call that the vector A1, A2. Now, there are many contexts in which points and vectors, we think of them as the same thing. They're exactly the same. But how we can write down a vector that goes from the origin and hits the point A2, A1, comma A2, is with angled brackets. And notice that this kind of tells you, gives you positional awareness. So this basically says you move A1 units to the right and then A2 units up, you would hit this point. So it coincides with the rectangular coordinate system. And we can actually write vectors as coordinates. So I can write the vector A is angled brackets A1, comma A2. Once we write angled brackets, it means I'm specifically thinking of this thing as a vector, not as a coordinate. And there will be times where it'll be important for you to distinguish. As far as a Calc 2 or 3 student is concerned, always distinguish between whether you're using a point or a vector. It's going to be very important. In higher mathematics, it actually doesn't really matter all that much. We think of them as the same thing. But for us, it will be very useful to distinguish between the two. For vectors, we don't really call these guys coordinates, so the A1 and A2, we would call them components. So I can say this is the first component, the second component. If we're in R2 or R3, we call this the X component, the Y component, the Z component specifically. So I mentioned that here. So that's just some naming things. So the vector 1, comma 2, comma 3 has X component 1, Y component 2, Z component 3. And I can sketch this vector. I can sketch it like a position vector. How would this vector look? Well, just as before, find where X is 1, find where Y is 2, then rise until we get to the level of 3. There's going to be a point here, 1, 2, 3. And so this is the point 1, 2, 3. Then I can think about the vector that goes from the origin hitting that point. This is the vector 1, 2, 3. Okay, so that's a picture of the vector. So we can have vectors in 3 dimensions, although normally it's very hard to visualize vectors in 3 dimensions just on their own. But yeah, that's an example of a vector. Now, one thing we're often going to be interested in is vectors that have a specific initial point and a specific final point. And it turns out that you can describe that vector by subtracting the final points from the initial points. So, for example, let's say I have a vector that it starts at the point 4, comma, minus 2, comma, 0, and it ends at the point 1, comma, 3, comma, 5. Right? So there's just this vector here. How can I write it down as something like X, Y, Z? Right? Now, it turns out this here is the final point, and this here is the initial point. And you can find the vector by taking the final coordinates or components and subtracting the initial components. So if I were to describe this vector, let me call it A. A is going to be equal to the final point, 1 minus the initial point, minus 4, comma, 3 minus a minus 2, comma, 5 minus 0. And that's the vector. So this means that our vector that goes from from this point and ends at that point, it will be minus 3, comma, 5, comma, 5 with angled brackets. So I want to distinguish. It is not the same as the point minus 3, comma, 5, comma, 5. It is the vector. It is the thing that moves. Essentially, you can think of it as moving 3 units to the left, well, if you're in the XYZ plane, this would move 3 units in this direction, 5 units in that direction, then up by 5 units. So it'll be the vector that hits here. Okay, so that is the vector. So that's how you can actually talk about a vector that has a specific initial point and a specific final point. Now let's talk about some properties of vectors. Now, because the length of a vector if I have a vector, the length of the vector is just the length between the final and initial points. Length of vector equals distance between initial and final points. So we can just use the distance formula here. So because I can think of the vector as a position vector, what I can do is just think of the point as 0. So by the distance formula, I can just take, if it has components A1, A2, and A3, it's just A1 minus 0 squared plus A2 minus 0 squared plus A3. Hold on, let me move this thing out the way here. Plus A3 minus 0 squared, right? And so we have this formula here. Now, when we talk about the magnitude of a vector, you can use absolute values to represent the magnitude of a vector. So this, or sometimes we use double absolute values for vectors, represents the magnitude of the vector, magnitude of A. Now, either one is fine. I'll normally use the single absolute values just because I'm lazy, but it's not strange to use a double absolute value when you're talking about vectors specifically, and use absolute values when you're talking about scalar things. Some people might do that, but they're interchangeable. As long as you represent the vector with an arrow, it's going to be understood that you're talking about the magnitude of a vector, not the absolute value of a function. So yeah, that's it. Now, how would you actually find the length? Let's actually just do one. What's the length of the vector that we did in the example above? So if we wanted, so if A was equal to the vector minus 3, 5, 5, this means that the magnitude of A is going to be, well, the square root of the first component squared plus the second component squared plus the third component squared. That's actually going to be 9 plus 25 plus 25, and that is the square root of 59. So this here is the length of that vector. So this I can think of as a certain direction, moving -3 in the x direction, moving 5 units in the y direction, then moving 5 units in the z direction. That is going to be how I think of where this guy is pointing. We can describe that with angles and so on and so forth later on, but for now, this is already a description of how it's moving. Now, if we wanted to know what is the length, if I think of this guy as a position vector, what is going to be the distance from the origin to the terminal point of the vector? Well, it's going to be radical of 59. Okay. So that's how we measure the length, just apply the distance formula. Let's move down to operations of vectors. Now, there are two main vector operations that are widely defined and are all thought of being the same thing. These operations are called addition and scalar multiplication of vectors. Meaning, if I have two vectors, and these should really be arrows here. So that's a typo on my part. So if A and B are two vectors, there is a notion of adding these vectors together, and there's a notion of multiplying a vector by a scalar. This is called addition and scalar multiplication, respectively. All right, so these are two very important vector operations. We can add two vectors together, and hence we can subtract them. I'll talk about that a little bit more. and we can talk about multiplying a vector by a number. Now, if I have given the component form of a vector, this is done in a very natural way. You add the corresponding components. If I want to multiply a vector by a scalar, you multiply the components by that scalar. Now, there are some things to note here. If your scalar is a positive number, your scaled version of the vector will have the same direction as the original. If it's a negative number, you would have the opposite direction of the original vector. And I'll talk about what that means in a little bit. And if you have the scalar is 0, you get something that's called a zero vector, with 0 with a little arrow over it. Now that's a whole other beast. It has no direction in all directions simultaneously. We'll talk about that moving forward. The zero vector is a very important vector, but it's very strange. It has no particular direction. The length of a scaled vector is just the real number magnitude of the scalar times the magnitude of the vector. And the vector a plus b is sometimes called the resultant vector, right? So adding vectors, let's talk about what this means geometrically. So let's say I have a vector a, and I have a vector b that looks like this. Then what does it mean to add two vectors? Well, it means to start at the initial point of A, go to the final point, and then I stick the initial point of B right there, and you just kind of pass the buck. So if you kind of travel along A, and then start B at that point, and then travel along B, the resulting vector, the vector that goes from the initial point of A all the way to the final point of B, that is the vector that's called A plus B. So that's geometrically what it would mean. And how do if I know the components of this is A1, A2, A3, and that is B1, B2, B3, what direction describes the sum? Well, you add the corresponding components, A1 plus B1, A2 plus B2, A3 plus B3, and so on and so forth. Now, I can talk about multiplying a vector by a number, and this really scales the vector. So, for example, here is my vector A. If I were to find, say, 2A, that is something meaningful. It's just I'm going in the same direction as A, but now it's stretched by 2. It's twice the length. So if this had length L, this is going to have length 2L, but same direction as A. If I were to say something like, what about a negative scalar? So like a minus 2A. Well, it literally changes the direction in the opposite way. So the initial point becomes the final point, and the final point becomes the initial point. It will also have length 2L, but it will be in the exact opposite direction of A. And this kind of leads to vector subtraction, right? So what does it mean to take one vector subtracting another? Well, we just think of it as adding the negative of the vector. So if I look at geometrically speaking, so if here's my vector A and here's my vector B, then negative B is going to be the guy that goes in the opposite direction. And so if I take A and then attach to that negative B, then the result of that is going to be the vector A minus B. And how do I find that vector? It's just subtracting the components. By the way, this vector A plus B, I mentioned it already, but let me just write it down. It's sometimes called a resultant vector in a physics context specifically. But this is the vector A plus B. So minus just means you go with A and you subtract B, which means you add to it the negative direction of B. Okay. So that's that. Two vectors are parallel. One thing we want to know is when vectors have essentially the same direction. They will be parallel if they are scalar multiples of each other. So A or 2A or minus 2A, these guys are parallel. These are all parallel. So if the direction is the same or you're in exactly the opposite direction, we call that quote unquote parallel. So that's an important thing to talk about, and we'll talk a little bit more about. Yes, so negative b would essentially, because it'll be scalar multiple. So if your b is b1 comma b2 comma b3, then yeah, negative b is actually going to be negative b1 comma negative b2 comma negative b3. Yes, so just, and not negative specifically, because if one of these were negative originally, then the negative of that would be positive, but you just literally negate all the components to find the negative of a vector. So the negative actually follows this definition here. Just think of a negative vector as -1 times a vector and apply that definition. Okay, moving forward. Here are some mathematical properties of vectors. Adding vectors in either direction, we'll get the same thing, actually. So here I looked at A plus B. If I took B plus A, I would have actually gotten the same thing. So if I looked at first do B and then do A, then the vector that I would have gotten here, it's actually going to be the same as that. It's the same as A plus B. You'll always get the same vector. So properties like this, these are things that you can do algebraically with vectors. And we're almost out of time, or just about out of time. So let's actually just run through a few examples of dealing with some specific cases of vectors here. So if you're given a vector A, which is 1, 2, 3, and a vector B, which is -4, 0, 5, compute the following guys. Okay, so let's actually just run through that. So it's nothing really complicated. It's just something that you should know, that we're allowed to do vectors in this particular way. You might also realize at this point, just to nip this in the bud here, that I didn't talk about multiplying two vectors together. I only spoke about adding two vectors together or subtracting two vectors together. This is because in general, there is no real multiplication when it comes to vectors. There is no real division when it comes to vectors. There are vector products that we will be taking in future sections called the dot product and the cross product, but these have a very particular meaning and interpretation. So I just want you to be aware of that. Multiplying two vectors, you kind of don't have that unless there's a very specific context. That being said, let's actually do these examples. So if my A is 1, 2, 3, then of course, the magnitude of A, we saw this already, it's the square root of 1 squared plus 2 squared plus 3 squared. So that's 9 plus 4, 13 plus 1, 14. So radical 14. Now, moving on to problem B, my A is 1, 2, 3, and my B is -4, 0, 5. What would A plus B, what would that vector be? Well, A plus B would be equal to, well, 1, 2, 3 plus -4, 0, 5. That is going to be, now you don't have to write out the steps all the time, but let me just write this in. Technically what you do is you take the 1 and you add to the -4, comma, you take the 2, you add it to the 0, you take the 3 and you add it to the 5. You don't normally have to show that working though. So ultimately you should end up with -3, comma 2, comma 8. If we look at C, C says we want A minus B. So it's a very similar idea. A minus B. This is going to be 1, 2, 3 minus 4, 0, 5. So this is going to be 1 plus 4, 2 minus 0, 3 minus 5. So you're going to have 5, comma 2, comma minus 2. (2a, 3b, and then 2a minus 3b. So if you had 2a, that just means 2 times 1, 2, 3. That is 2, 4, 6. And again, you could think of this as being 2 times 1, 2 times 2, 2 times 3, but you don't really have to write that out. E, if you have 3b, well, that's just equal to 3 minus 4, 0, 5. This is going to be minus 12, 0, 15. Writing with the angled brackets. F, if I have 2a minus 3b, this just means 2 times 1, 2, 3, minus 3 times minus 4, 0, 5. And then, yeah, so that is 2, 4, 6. Minus that. Which is going to be 14, 4, and 6 minus 15. So you have that. So hopefully that was clear. We'll stop there. We have some more stuff to cover in a future section, but I would leave that for the section where we're going to talk about standard basis vectors, the I, J, and K guys. Those guys are going to be important, very important. In the near future. It's also going to give us another notation for writing down vectors. And then we'll talk about unit vectors, and that will actually end this section. Yeah. So that's vectors. Again, starting from the very beginning, know what it is. Something with magnitude and direction, we call it a vector. The position that it's in doesn't really matter. The direction and magnitude matters, but if we fix the position such that the initial point is the origin, we call that a position vector. Position vectors are super important. A lot of things are described in math as a position vector. So you can draw it in 3D here. This is a component way of writing a vector, just with angled brackets. You can connect a vector from one point to another point by subtracting the final point minus the initial point. You can find the magnitude using the distance formula. That's going to be important from time to time. And this is how we can scale them or add vectors together or subtract them. We don't really have vector multiplication, but otherwise the properties are this guy. Computationally speaking, dealing with vectors is very easy. But again, these guys are all associated with a certain picture. These guys are arrows that are moving around in space. So hopefully that is all clear. I will post a PDF of this when I post the video for anything that was missing. But so far, any questions before we wrap up? General questions or questions about anything that I spoke about here? So in today's class, we looked at the basics of the three-dimensional space, how to navigate it, how objects would look in this space, and what we call certain things. Then we looked at vectors, which is another kind of object. a lot of times we're going to describe things in 3 space using vectors. So we need to know about vectors, how they work, how to use them, how to do math with them. Very, very important. And yeah, so otherwise, any questions moving forward? Quick question. Are you putting bonus questions in the exam? Yeah. Yeah, the exam is pretty much going to be like an in-person exam. I think I messed up the view here. Okay. So that being said, you guys can, I knew you were interested in kind of putting together some kind of Zoom study group or something, as well as, I mean, I still have office hours through Zoom. I've only had one person, well, 2 people really reached out to me during office hours. So, but that's still a thing. So I'm still holding office hours during the regular time. I sent the link a while back. But if you want to meet me during office hours, just shoot me an email and say, hey, and I'll resend you the link if you lost it. But that being said, just going to wrap up. So by early next week, you'll hear about the exam. Exam 1 is going to be April 30th for you guys. Exam 2 is going to be the last day of class, which is around May 15th or so on and so forth. Information's on specifics about the exam will be given to you by early next week, and then by the end of the following week is when you have the first exam. What we're doing for the final, I do not know. This class has a departmental final. I don't know if they're still sticking with that whole departmental final structure, but whenever I hear from them, I will let you guys know. In the meantime, I'm moving forward with this because I can't wait on the math department to actually tell us what they want us to do for exams. They're really dragging their feet here. But yeah, that being said, we will kind of wrap up there unless there are any final parting questions. Yes, Mohammed, what's your question?
So for the P or F grading, do I have to tell you about this, or do I have to talk to the financial aid?
Oh, I think you can ask about that. And if you're worried about how that will affect your financial aid, you should probably talk directly to them. That being said, there are a lot of drawbacks to a pass-fail grade, but I believe that most of the consequences are actually withdrawn for this semester because you have special circumstances. So before, usually if a course was required for your major, you couldn't do it, but I think they're kind of letting that slide. I don't think there, and don't quote me on this, check it, but I don't think there would be any financial aid consequences either way. I don't think there ever would.
No, my question is like, after we get the letter grade, do I have to tell you that I want the P or F or the letter grade, or should I tell to the other people? I don't know.
That's something that you should let the registrar know about. So definitely do the registrar. And,
oh, okay.
Yeah. So you'd have to go to the registrar. In terms of the letter grade, yeah, they're the ones who you want to contact. So it's something that you should apply for directly with the registrar if you want it. And you says you have 2 weeks after grades to decide with the registrar. I don't know, but maybe you can double check on that. But yeah, in terms of the usual drawbacks or consequences of pass-fail grades, I believe they're relaxing all those consequences for this semester. So I guess that's it. Anyone interested in a Zoom study group? You can hit Mohammed up. He put his number in the chat there. So make sure you copy that. For privacy reasons, I don't really post the chats publicly. So if you're interested in that, you should probably copy his number down right now. I will extend the homework due dates for chapter 12.
Also, is there any way you can open up the previous homeworks, like from the integral and stuff like that, so we can review them?
You should be able to review them either way. Like, if you have attempted them, you should be able to review them. If for some reason you can't view a past homework, then that's an issue that you should probably check with technical support or customer service about. But from my end, I set it so that anyone can view past homeworks. So you can't submit the homework late, but you can definitely look at previous problems for practice sake. That being said, I think if you want extra practice, practicing from the textbook is a good idea. Just practice similar problems in the current sections. And you would start there. Okay. Yeah, so someone mentioned here, if you go through study plan, through the study plan tab, you should be able to look at past assignments. But yeah, I know everyone should be able to do that. Nothing should prevent you from seeing a past homework. Okay. That being said, I think we'll sign off. Thanks for showing up, everybody. Stay safe, keep studying hard. I will let you guys know more detailed information about the exams early next week. Have a good day and good rest of the semester. Let's finish this thing off strong. All right. Take care and bye, everyone. Again, last chance to kind of take Mohammed's information down if you're interested in a study group. But I will end the meeting right now. So I am going to stop the recording. So bye, everybody. Take